Welcome back, Pre-Calculus. Today we're going to be reviewing functions algebraically and graphically. I've got the checklist on the screen. You know what to do from here. So let's first kind of remind ourselves about the vertical line test. You don't need to write anything down yet, but we know that a function can only have one y value for each x value, right? So let's write that. So that's how we define a function. So if a vertical line intersects a graph in more than one point, then the graph doesn't represent a function, right? Because if I have something like this, for example, notice that if I can find vertical lines that cross at more than one location, right? So for this particular x value, and a vertical line is an x equals something, right? We cross at more than one, so this would not be a function, right? However, if I drew something like this would pass the vertical line test because any vertical line I pick would only cross the graph once. Force a pause on your screen. Can you try example 1 for me, just kind of a review? Read the directions and see if you can figure out these 4 graphs. Grab a different color pen and hit continue when you are ready to check your answers. All right, here are some possible answers. Of course, answers may vary. So here's a graph that passes the vertical line test. So it is a function, has 1, 2, 3 x-intercepts. This one passes the vertical line test, 1 y-intercept, no x. This one does not pass the vertical line test. Now, for example 1, part D, a function that has 2 y-intercepts, well, that can't happen, right? So here, as soon as I make my 2 y-intercepts, I already don't pass the vertical line test. So part D is impossible, okay? So this guy doesn't work. Force a pause on your screen. Can you please copy the 2 functions I have in your notes? Okay, so we're going to review domain and range graphically here in just a moment, but I first want you to kind of think about this algebraically, like when do we have problems with our real numbers, okay? So if I take a look at this first function, is there any x I could plug in and have any kind of problem? Like, is there any real number that I can't square or that I can't multiply by 3 or I can't add? No, right? This has no problems. I can plug in any value I want for x and still get a real number out. So in this case, my domain is all real numbers. Remember, we can write that with like a double-stemmed r, or we can go negative infinity to positive infinity, either way, okay? Now let's take a look at the second function here. F of x is x minus 3 all over x squared minus 9. When would we have problems here with real numbers? Well, remember, I can't divide by 0, and this is a fraction. Remember, 0 on bottom is a no. So anywhere I have any x that would make the denominator 0 would be a problem. Okay, so I would need to exclude that from my domain. In calculus, we call those discontinuities. In algebra, we call those values that we need to exclude from our domain. So what I'm going to do is I'm going to take the denominator and see what values would make that 0, right? So x squared minus 9 equals 0. You could factor this if you want, or you could add 9 to both sides and then square root. I'm going to go ahead and factor so I don't drop my plus or minus. So now I factored, I can see, okay, this is going to be 0 when x is negative 3 and positive 3. So in calculus, that's what we call our discontinuities. That's where we have gaps in our domain. So in algebra, if I want to find my domain, it would be all real numbers except negative 3 and 3. So our domain would be negative infinity to negative 3. Then I'm going to do a parenthesis, okay? Then you can do a comma or a U union. Then I'll grab all the numbers from negative to 3, parentheses, because I don't want to include negative 3 or 3, right? U, and then 3 to infinity. All right, so that would be my domain, also known as all real numbers other than negative 3 and 3. Force pause on your screen. Can you just do a rough sketch of the rational function graph that I have here? Okay, so let's talk about domain and range graphically. Remember, domain, is that the set of all x's or the set of all y's that your graph covers? Those are your x's. So we're going to go from left to right, and we're going to talk about which x's are covered in this graph. So let's grab this pencil here. So what I would recommend us do first is let's go ahead and draw in the asymptotes so that those are a little bit clearer. Remember, an asymptote is a line that your function approaches, right? And horizontal asymptotes you can actually cross, but you cannot cross vertical asymptotes. So let's go ahead and draw in the asymptotes here with dotted lines, okay? All right, so you can see that we've got a horizontal asymptote of, what is the equation of the horizontal asymptote? Can we tell here? Yeah, that is going to be y equals -2. Oh, sorry, -3. And what about the vertical asymptotes? What are their equations? We've got x equals -1 and x equals +1, okay? So let's talk about domain. We're going to go from left to right. So notice if you look at kind of this piece in the left-hand corner here, those are going from x equals -infinity all the way until that first vertical asymptote, which we said was -1. And we want a parenthesis there because we don't want to include -1, right? So now you can do a comma or the union symbol. And now we want to take this middle piece here, and those are x's going from -1 to 1, and would you want parentheses or brackets there? Parentheses again. Again, we're not including those values, right? A bracket would imply we're including them. All right, now another union, and now let's go to this bottom corner here, and we'll have x going from +1 to +infinity, parenthesis or bracket, parenthesis on both. And remember, always a parenthesis with infinity since it is not a number. All right, now let's talk about range. Remember, range is your y, so we're going to go bottom to top. So do you have a lowest y value, or do you go down forever on this graph? We go down forever, so we're going to go -infinity. And then we reach -3, y equals -3. Parenthesis or bracket. Parenthesis there because we never quite touched -3, right? Now we've got some empty space, and we pick back up at y equals what? Y equals 0. Now parenthesis or bracket there. That's going to be a bracket because you do include 0. And then do you have a highest point, or do you go up forever? We go up forever, so that'll be infinity with a parenthesis. All right, so that's the algebra. Let's connect this to some calculus now. Will you write this, please? A function is continuous if, and this is in the layman's terms, if you can draw it. So if you can draw the function without picking up your pencil. Okay, kind of a generic definition there, but very important concept in calculus, okay? So anywhere you would have to pick up your pencil, again, going left to right, that would be, not surprisingly, called a discontinuity, right? So if we look here, I can draw this piece, and then I have to pick up my pencil, right? And then I can draw this piece, and I have to pick up my pencil, and then I've got this last piece. So I have discontinuities here at x equals -1 and 1. In other words, the pieces I had to leave out of the domain, okay? So if we were to come back here, the pieces I had to leave out of the domain for this rational function were wherever the denominator was 0, right? -3 and 3. Well, that's what we call it in algebra, the gaps in our domain, right? In calculus, we call those our discontinuities. Okay, so let's put that in our notes as well. Can you write this for me, please? In a rational function, a discontinuity occurs when which piece is 0, numerator or denominator? When denominator equals 0. Okay, and then we've got two kinds of discontinuities. I'm going to tell you the names, and then we're going to look at how do we classify them. But they're called removable, or very creatively, non-removable. All right, so go ahead and pause your screen if you need any more time on this slide. All right, so I'm going to go ahead and force a pause on your screen and copy these real quick in your notes, and then we're going to classify these as removable or non-removable. Okay, we are back. So first of all, we've got 5 pictures here, and one of them is actually continuous, okay? So which of these 5 can you draw without picking up your pencil? It will be option E, right? So this guy is continuous. All right, now the other 4 have a discontinuity, and discontinuities are either removable or non-removable. They're removable if they're just 1 point away or 1 point removed from being continuous, okay? So in other words, I can slide or add 1 single point and it would make the graph continuous, Okay, so with that definition, there's 2 remaining that are removable. Can you guess which 2 are removable? It will be B, because I can patch that 1 point up, right, to make it removable, and it will also be D. Again, I can slide this point up, and now it would be nice and continuous, okay? Now, anywhere you have a jump, this is called non-removable. So let's go ahead and classify those in your notes, label those. So in this case, A and C are both jumps, and that's called a jump discontinuity, which is a kind of non-removable discontinuity, but B and D are both removable, okay? All right, go ahead and copy f of x in your notes, and then we're going to work example 4 together. All right, so it says decide if there's a discontinuity at x equals 0. Remember, to do that, we just set the denominator equal to 0, okay? And then we want to label that discontinuity as removable or non, okay? So let's set the denominator equal to 0 to check, is there a discontinuity? Well, the denominator is x. Setting it equal to 0, that means x is 0. Yes, there is certainly a discontinuity at x equals 0. Now, if I want to label this as removable or non without looking at the graph, what we want to do from here is factor both the numerator and denominator if possible. So the numerator factors as x, parentheses x plus 2. Denominator is still just x. Now, take a look at this. My discontinuity came from the factor of x. Now I can remove that factor. So, because I can remove that problem factor of x, this discontinuity is indeed removable, okay? Let me show you the graph to convince you. So here's a graph of that f of x. It looks continuous, but let's get closer on x equals 0, and you'll see, oh, there is a hole there actually, right? So I do have a discontinuity at x equals 0, but notice it's removable because I can patch that with just 1 point. Now, an example of a non-removable, if you want to write this, would be something like f of x equals x plus 5 over x minus 2, for example. So when I set the denominator equal to 0, I get that my discontinuity occurs at x equals positive 2. Notice there's nothing to factor. These don't cancel. X plus 5 is not the same as x minus 2, so this is going to be a non-removable discontinuity. And you can see that graphically here as well. I would have to pick up my pencil at x equals 2, and notice I cannot nicely patch up that asymptote, right? So this is a non-removable discontinuity at x equals 2. I'm forced another pause on your screen. Can you please copy this function, and can you go ahead and graph it either on Desmos or on the 84? If you don't know how to find the absolute value buttons on either, I have put those in kind of that teal handwriting there. All right, so I've got f of x graphed here on an 84. You may know this is that the minimum is 2, negative 1, but I do want to show you how to find that on an 84. Of course, on Desmos, you can literally just click that button, that min, right, and it'll tell you the ordered pair there. On an 84, you're going to go second, trace, and we want a minimum, so we want number 3. And it's going to ask for a left bound and a right bound. So I'm going to go close, but to the left of that minimum, and then hit enter, and I'll give kind of a guide there. Okay, I can see I'm to the left of it. Then notice on the bottom here, it's asking for a right bound. So then I'm going to get close, but to the right. And then it says guess. I do want you to guess, so hit enter again. And it's giving me the minimum. Notice that if I were to round to 3 decimal places, I would have 2, negative 1. So that is our minimum. And then if we want to talk about increasing, decreasing, we talk about our x values, okay? So the x values for which the y's are decreasing. So if I am going from left to right, I'm decreasing on this, if you want to call it, it's a linear piece here. So those x's go from negative infinity to positive 2. And then we switch to increasing, so positive slope from x is equal to 2 to positive infinity. So let's write our answers here. So the local min or max, so we had a local, just means relative. So we had a local min, and the ordered pair there was 2, negative 1. Our function was increasing from x equals negative infinity to positive 2. Now, my MATLAB is going to ask that you put a bracket on that positive 2. I hate that, because then when you do this was the decreasing part. So let's go decreasing from negative infinity to 2, and then we're going to go increasing from 2 to infinity. Again, it wants a bracket here. This is actually a point of mathematical debate right now. I disagree that you can be decreasing and increasing at a singular point. On the AP exam, they'll take either brackets or parentheses because it is a matter of debate, but my MATLAB wants brackets there. So just FYI, make sure you're doing brackets on increasing and decreasing. Where was this constant? Nowhere did we have a horizontal line, so there was no constants for this particular graph. Force a pause on your screen. Can you try this one on your own? All right, go ahead and check with your different color pen or pencil. I've kind of tried to color code here for you. Again, notice I'm basically giving the domain for the pieces where the function is either increasing, decreasing, or constant. Okay, I'm going to force a pause on your screen. Can you please copy the definitions I have for even functions? All right, so an even function is a function that's symmetric with respect to the y-axis, like cosine of x was even, right? In other words, whether I evaluate at positive x or negative x, I get the same y value. So like y equals x squared is an even function because both 1 and negative 1 have the same output, right? Both 2 and negative 2 are both 4 on this graph, okay? So the way we test this is this right here. I'm going to plug in negative x and see, do I get the exact same thing as what I started with, okay? So let's show this f of x. Will you please write f of x as x squared plus 5? To verify algebraically, again, what we're looking to test is what is f of negative x. If I get the same thing as what I had for f of positive x, then the function is indeed even, okay? So anywhere I see an x, I'm replacing it with negative x in parentheses. So I'm replacing that x with negative x, and then I still have the plus 5. Well, a negative squared, is that positive or negative? That's positive, so this is equal to x squared plus 5. Well, is that what you started with? Yes, it is. So since they're the same, this function is indeed even. Now, if we have even functions, of course, we have odd functions as well. So I'm going to force a pause on your screen. Please copy these definitions. All right, so an odd function would be like sine of x or y equals x cubed, okay? Because whatever you plug, if you plug in 1 or negative 1, you get exact opposite outputs, okay? If you plug in 2 for x and negative 2 for x, again, you get exact opposite y value. So one's positive 8, one's negative 8, but the absolute value is the same, okay? So we're going to start it out the same way. We're going to test f of negative x. So anywhere I see an x, I'm replacing it with negative x. But this time, instead of getting the exact same f of x that we started with, we would get the same thing but with a negative factor, negative 1 factor on the outside, okay? So let's try this. Will you please write this f of x in your notes? So we've got x cubed minus x. We test the same way, okay? We test by replacing each x with a parentheses negative x. Then we clean it up, okay? So a negative cubed, is that positive or negative? That's negative, right? It's the same as that. Then I've got a negative times a negative, which is positive, okay? Now look at your original. Is this exactly the same as what I started with? No, it's not. So it is not even, okay? Now what you try to do is you factor out a negative 1. This would give me x cubed minus x, okay? Now is that what I started with? Yes, it is. So it's odd because I got exactly opposite, O, odd, O, opposite and origin from what I started with. All right, here's our final example. I'm going to force a pause on your screen. You tried this one. So evaluate f of negative x. See if it's even, odd, or neither. Remember, if you get exactly the same thing as what you started with, it's even. If you get the same thing but with a factor of negative 1, it's odd. And if you get neither of those, then it's neither. All right, here's what I got when I plugged in negative x for both of my x's here and here. Make sure you're using parentheses. Then I cleaned it up. So a negative number to the 5th power is going to be negative. So I cleaned it up, brought that negative in front. This piece will also be negative, but then times another negative makes us a plus x to the 7th. So now take a look at this. Is this exactly what you started with? No, it's not. So it's not even, because when I test both the positive x and a negative x, I don't get the same y value, okay? So now try factoring out a negative 1. When I factor out a negative 1, this becomes positive 3x to the 5th, and this becomes minus x to the 7th. So now take a look at that. Is that what I started with? Absolutely. So it's exactly opposite of what I started with, so this is odd. All right, you all, that is all we have for today. Please write a summarizing sentence, and I will see you all next time.